R2, real numbers and their properties. So now we're going to talk about real numbers and a bunch of different properties associated with real numbers. So we should talk about some of the basic sets that are part of real numbers. Now we already talked about natural numbers. Right, with that bolded N. And we said the natural numbers were the numbers, or counting numbers, 1, 2, 3, 4, right, going on forever. So our natural numbers. Another one that we should be familiar with are whole numbers. Remember, your whole numbers are just your natural numbers and 0. So your whole numbers, and no, we don't have a special capitalized or bolded letter that we use for that. Integers. So integers, we use a bolded capitalized Z. So integers are basically your signed whole numbers. So add minus signs and plus signs. So we have, I'm going to do an ellipsis beforehand and get rid of what looks like a summation. So ellipsis, -3, -2, -1, 0, 1, 2, 3, dot, 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 ellipsis, right? So those are your integers. Now, integers, like I said, they're signed whole numbers. Rational numbers. Rational numbers, we use a bold or capitalized Q. So, rational numbers. Rational numbers are any numbers that can be written in the form P over Q such that P and Q are integers. P and Q are integers, and Q is not equal to 0. Which should make sense because you can't divide by 0. So rational numbers can be written in the form P over Q, where P and Q are integers, and Q is not equal to 0. Remember that rational numbers will always either terminate or repeat. So at some point, they get to the point where they just repeat a number or a set of numbers over and over and over again forever. Or they will terminate, meaning that eventually when you do that division, your division will stop. You have nothing left but 0. Those are your rational numbers. Then you have irrational numbers. Irrational numbers are the complement of Q. Right, they're the complement of the rational numbers. If a number is not rational, then it must be irrational. And remember, we are still focusing on real numbers. So, real numbers and we use a bolded capital R for real numbers. Real numbers include all rational and irrational numbers. So real numbers are all rational and irrational numbers. So how does this all come together? Well, let me show you. I'm going to do a little tree diagram here. So we start out with real numbers. And real numbers can be split into rational numbers and irrational numbers. We're going to stop that side. Rational numbers can be split into integers and non-integers. Integers can be split into whole numbers and negative integers. Right, we whole numbers are 0, 1, 2, 3, 4, 5, 6. Negative integers comes for everything else. So whole numbers are your non-negative integers. And then your whole numbers can be split into 0 and your natural numbers. Right? Natural numbers are your counting numbers, 1, 2, 3, 4, 5, 6, etc. Add 0, you get the whole numbers. Take your whole numbers and add the negative integers, which are your signed whole numbers, and you get integers. Take your integers and your non-integers, and that puts you into rational numbers. Rational numbers and irrational numbers take you to the real numbers. Are included in that. Now you may say, well, wait a second, non-integers, irrational numbers are non-integers too, right? Think of this as a classification under rational numbers. Irrational numbers, by definition, are non-integers. They're irrational. That's all there is to it. So when we start breaking up the rational numbers, that splits into integers and non-integers, etc., etc., etc. Okay, so those are our sets and how they relate to each other. Let's get into some other things about real numbers that you should be familiar with. Well, what about exponents? At this point, you should be familiar with exponents, but just to make sure, if we have a to the n, a is called the base, and n is the power or the exponent. And all that means is to take a and multiply it by itself n times. Now when I say multiply it by itself n times, I really mean multiply together n a's, or n of the base. So if I have 5 cubed, that says take 3 5s and multiply them together. I word it that way because if you say, people tend to say, take this number and multiply it by itself 3 times. Well, you're really only multiplying twice. So you're multiplying 3 of these base numbers together. 5 times 5 times 5 gives you 125. So that's why I word that particular way. Okay? So there's exponents. What else should we be familiar with? Well, you should also be familiar with order of operations. Now, many of you are familiar with PEMDAS, right? I sometimes like to say PEMSA. Now you're familiar with, please excuse my dear Aunt Sally. The reason I tend to mix it up a little bit here is because I want people to remember that multiplication and division are equal operations get done at the same time, going left to right. And then addition and subtraction are equal operations done at the same time from left to right. Too many times I see people determine that they have to multiply before they divide. Because they know, please excuse my dear Aunt Sally. Parentheses, exponents, multiplication, division, addition, subtraction. And they're determined they have to multiply before they do any division. That is not the case. M and D happen at the same time. Once you get down to your multiplication division, you start from the left and do any multiplication or division that you come through. Same thing with addition and subtraction. When you get to that point, addition doesn't necessarily come first. It's working your way from left to right, doing any addition or subtraction you come across. That's why I tend to do the PEMSA, because it doesn't matter multiplication, division, division, multiplication, whichever you come to first. It doesn't matter addition or subtraction, subtraction or addition, whichever one you come to first. And that's why some people are nowadays teaching things that are more like gemma or gemma, which says, first of all, grouping, instead of just specifying parentheses, where we end up having to say there's a lot of implied parentheses, right? If I have 3 plus 2 over 7, division comes before addition, but there are implied parentheses here, right? Well, this says grouping. Anywhere I would have said there are implied parentheses, now we look at it as there's the grouping. 3 plus 2 is grouped together in the top of this rational function. So we would add 3 plus 2, giving us 5, and then divide by 7. So grouping. E for exponents, so that doesn't change, but now we just have the M saying multiplication and division. They're done at the same time, multiplication, division. A for addition and subtraction. Done at the same time, addition and subtraction. So there's order of operations. So you want to make sure that you keep that in mind and get those done correctly. So now we're going to switch over to properties of real numbers. Some things that we need to keep in mind as we're working with them. Okay, so properties of real numbers. And we're going to assume that A, B, and C are real numbers. So let A, B, and C be real numbers. So each of those represents a real number. Closure. Closure means that when if an operation has closure, when you perform that operation on a certain set or two pieces of the same set, then the result will also be in that set. So if we're dealing with the set of real numbers, addition has closure on the set of real numbers. If you add any two real numbers together, then you will get a real number as a result. Subtraction also has closure on the set of real numbers. Because when you subtract one real number from another real number, you get a real number. Multiplication, division, all of these have closure on the set of real numbers. But realize that they may not on other sets. So let's say we're looking at the set of integers. Set of integers, any integer plus another integer gives you an integer. Any integer minus another integer gives you an integer. Any integer multiplied by another integer gives you an integer. But an integer divided by another integer does not always give you an integer. Therefore, integer, the set of integers, does not have closure over division. If I was dealing with whole numbers, then add a whole number to another whole number, you get a whole number. Subtract a whole number from another whole number, you may not get a whole number. Multiply a whole number by another whole number, you're going to get a whole number. But if you divide a whole number by another whole number, you may not. So over the set of whole numbers, there is only closure for addition and multiplication. So closure means that when you perform the operation on values within a certain set, the result will also be within that set. Commutative properties. Commutative properties, you should be familiar with these. Sometimes we refer to them separately as the commutative property of addition and the commutative property of multiplication. Any real number plus another real number is going to have the commutative property, meaning that A plus B is equal to B plus A. We can add them in either order and it does not change the result. And that works for any real number, and that works within the sets too, that as long as you can reverse the order of the addition and it's going to work. Also, that's the commutative property of addition. The commutative property of multiplication, A times B is equal to B times A. We can change the order of the addition or multiplication to get the same result. Commutative property. The associative property. Associative property, I always look at the associative property as kind of being a special case of the commutative property. Just says that if I have A plus B plus C, that's the same as A plus B plus C. We associated these two together first, and then this one, so we add A plus B and then we add C. Here, order of operations says we add B plus C and then we add A. Obviously, it's going to come out to be the same result. Same thing happens for multiplication. AB times C is equal to A times B times C. Or actually, let me put it this way to make it a little clearer here, to force that. A times B times C is equal to A times B times C. And remember I said I can treat this as a special case of the commutative property, that really what we're doing is we're just changing the order of them. A times B times C, I can multiply A times B times C, or I can move them and multiply B times C times A, it doesn't matter. Commutative property, associative property, only good for addition and multiplication, not good for division or subtraction. But remember with both of these two, that any subtraction problem or division problem can be changed to be written as an addition problem or multiplication problem, in which case commutative and associative properties will work. Inverses. Inverses, when you're dealing with addition, you have the additive inverse, which means if you have A, the additive inverse is negative A. It's whatever you must add to it to make it equal to 0. So negative a would be the additive inverse of a. So 5 plus negative 5 gives us 0, additive inverse. Whereas in multiplication, a times 1 over a is equal to 1. So the multiplicative inverse is whatever you multiply a by to get a result or a product of 1. So in addition, additive inverse will make your result 0. Multiplicative inverse will make the result 1. And then distributive property, so the distributive property, sometimes referred to as the distributive property of multiplication over addition, says that a times b plus c is equal to a times b plus a times c. We can distribute this a that's being multiplied by the sum b plus c by multiplying a times the first term b plus a times the second term c. So the distributive property allows us to stretch these things out and make it where we can utilize them a little differently. And as you know from past experience, this is what gives us the power to do a lot of things in algebra, to move things around and manipulate our equations to solve for any particular variable. Simplifying expressions. Okay, sometimes we have expressions that just need to be simplified. We want to make them easier to see, and so maybe we have 8 times x plus 2 minus 4x plus 3. And I want to simplify. Well, I can use some of these properties and say, well, wait a second, 8 times x plus 2, well, that's distributive property. I can say that's 8x plus 16 minus 4x plus 3. And then I can combine like terms, right? I see I have 8x's and I have 4x's. So I have 8x's minus 4x's gives me 4x's. I have 16 plus 3, so plus 19. So we're able to simplify that expression. So basically you want to get it down into the smallest number of terms possible without violating any rules. Remember when we talked about subsets and elements, and I talked about with subsets the difference between that sideways U, which was a strict subset, and the sideways U with a line under it saying that it could be the same set? Well, let's talk about inequalities. So inequalities, we have A less than B, which says that A is more negative than B. It can be positive. It's more negative, or if I put a number line here, all it says is that A is to the left, and that's negative, that's positive. A is to the left of B on the number line. A less than or equal to B means A is either to the left of B, it's either more negative, or it is the same as B. A greater than B, so A is more positive than B, so it would be to the right of B on the number line. A greater than or equal to B. So A is either going to be to the right of B or the same spot as B on the number line. Now, when we're dealing with these, what you really want to remember is that there are a nearly infinite number of ways that you can express these inequalities using the English language. So some of those might be, this is A less than B, A under B, A is not as much as B, A is fewer than B, right? A is at most B, it can be less than or equal to, A no greater than B, no greater than, meaning it's not greater than, but it could be less than or equal to, less than A less than or equal to B, right? A is more than B, A is greater than B, A is above B, A is at least B, greater than or equal to, A is greater than or equal to B, gray is more than B or the same as B, right? And there's a lot of different ways that these can be worded, so you always have to be careful about the wording of the questions to make sure you know which inequality you're dealing with. I see a lot of people make mistakes with that. Absolute value. Absolute value. Now I'm hoping by this point most of you are going, come on, Mr. Davis, we already know these things. And that's a good thing. Remember, this is a refresher or a review. All of these things should be familiar to you. We just want to make sure that you're still familiar with them. So absolute value, and we do that by saying, putting two vertical lines and putting your, whatever you're taking absolute value of in between. So that says the absolute value of A. Now let's assume that A is a non-negative number. Actually, let's just say a positive number. Because that gets 0 out of there too, because the absolute value of 0 is 0. But if A is a positive number, then the absolute value of A is going to be A. If A is a positive number, then the absolute value of negative A is going to be A. If A is 0, then it's 0. So basically, all absolute value does is it strips away the sign. It's not negating it, it's not finding the inverse. All it's doing is removing the sign. So if a number is already positive, it stays positive. If it's negative, it becomes positive. If it's 0, it stays 0. So it's just getting rid of any sign. Okay? So, very useful there. Let's take this a little further though, and bring in these inequalities. Let's see what happens if I say the absolute value of A, let's say the absolute value of A is greater than or equal to 0. The absolute value of A is greater than or equal to 0. Well, what could be A? Well, if I say it's greater than or equal to 0, isn't that all real numbers? Any real number, when I take the absolute value of it, is going to give me either 0 or a positive value. Negative A is equal to A, assuming that, or actually let me do this, is equal to the absolute value of A. So you have the absolute value of negative A is equal to the absolute value of A. Doesn't matter whether A is positive or negative. Because if A is positive, then this is going to be a negative value. When you take the absolute value, you're going to get a positive value. If A is positive here, then this is going to be a positive value. Take the absolute value, it's going to give you the positive value. So the absolute value of negative A is always equal to the absolute value of A. The absolute value of A times the absolute value of B is equal to the absolute value of A times B. Doesn't matter whether A and or B are positive or negative, because we know that when you multiply two numbers, if they have the same sign, the result's going to be positive. If they have different signs, the result's going to be negative, but we're taking the absolute value. So if these are both positive, then we're going to get a positive result. If those are both positive, we're going to get a positive result. If these are both negative, then this is going to make it where they come out to be positive. And if these are both negative, it's going to come out positive. If one of these is negative and the other one is positive, the absolute values are going to turn them both into positive. If one of these are negative and the other is positive, then the result's going to be negative, but the absolute value is going to turn it into positive. Okay? And then, just trying to see what I had here. Okay. Absolute value of A over the absolute value of B is equal to absolute value of A over B. Same idea. When you're dividing sign numbers, if the signs are the same, then the result's going to be positive. If the signs are different, the result's going to be negative. But the magnitude of it does not change. Therefore, it will work out to always be a positive result. Okay? Now here's another one that may be a little different to you. You may not have seen it before. And this was actually based on Chevyshev's work called Chevyshev's Inequality. The absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. Sorry, that's supposed to be a B. The absolute value of A plus B is going to be less than or equal to the absolute value of A plus the absolute value of B. Now, if you think about it, that should make sense if you're dealing with signed numbers. If you're adding two numbers with the same sign, then you're going to just add them and keep the sign. So in this case, it doesn't matter whether the signs are positive or negative. By the time they get done taking the absolute value, it's going to be positive. So therefore, this is going to give you A plus B. Okay? So it's going to add those two numbers together. Over here, if the signs are the same, then you're going to add them, and you'll get the same result as if these signs are the same. If the signs are different, you're going to subtract them, and then the absolute value is going to take away the sign. Well, if you subtract them, the number is going to get smaller than the sum of them. Right? It's going to find the difference, so this number is going to be smaller than the sum of A plus B without any signs. So therefore, it could be less than or equal to. And if you think about that, then you come up with, you can see that this inequality works, that whether you're adding or subtracting them, you're never going to come out with a number greater than this, but you may end up with a number less than that. So let's say I look at A is equal to -5 and B is equal to 2, just to show as an example. Obviously, there is no way I can prove by plugging in numbers. I just want to demonstrate an idea of what happens. So if I take A is equal to -5, B is equal to 2, then I have the absolute value of -5 plus 2, and absolute value of 5 plus the absolute value of 2. And we're saying that it's going to be less than or equal to. -5 plus 2 gives me -3, so I have the absolute value of -3 less than or equal to, well, absolute value of 5 is 5, absolute value of 2 is 2, so I'm just going to make that 5 plus 2. Absolute value of -3 is 3. And then 5 plus 2 is 7. And we see that 3 is less than or equal to 7. So just a demonstration of what it's actually doing here, and you can see, yeah, if you're finding the difference between two numbers, you're going to get a smaller value than if you were to add the two numbers, or add the absolute value, I should say, of each of those two numbers. So that is always going to work. So there are some properties of real numbers.